Hey everybody, and welcome to episode number 123 of TGIK. I hope you're all having a great Friday. Let's see who's with us. We got Rodolfo signing in. We got Waleed saying hello from the Eastern Province in Saudi Arabia. Good to see you, Waleed. Got people checking in or signing in a little bit late here on Friday. So this is going to be a continuation of the DNS stuff that we talked about last week. We're going to dig more into DNS. We're going to play with node local DNS cache. We're going to kind of explore all of those things. And so if you haven't seen the previous episode, I definitely recommend, if you're watching the recording of this, that you should pause, go watch TGIK 122, and then come back and watch this one, which is a continuation of that episode. So good to see you all. We got Martin Borgman saying hello from the Netherlands. Jeremy Pruitt, who's somebody I've learned tech stuff from, good, saying hello. We got VJ saying hello, folks. Limati checking in. Good to see you, Limati. And Morteza from Tehran. Always awesome to see what a global audience we have. You know, I feel like I say that every episode, but it never really gets old for me. Fully Geared Bear from Portugal. And Joy from Richmond, Virginia. All right. Well, let's get into our notes. As always, our notes are up and public at tgik.io/notes. And so if you want to put a link in there or anything else like that, go ahead and put it in there. Mr. Keith Lee saying hello from Ireland. Good to see you, Keith. You're definitely in the top 5 of my favorite Irishmen. You know. Thank you for the link. Mr. George Castro is hanging out with us, and he put a link to the previous episode. You can also always just navigate to it using the shortcut, which is tgik.io 122. Would take you right there. So this week in the news, we got the K8's core. We have a 119 release candidate 0 that's live, which is pretty exciting. And so if you're interested in understanding more about what's coming in 119, definitely check out the 119 change log. There are looks like that's a good point. They do kind of bubble up, don't they? Okay, so release candidate alpha. I guess we can watch from the most previous change log. Got some scheduler changes. Got some configuration changes on the kube scheduler configuration. Certificate signing request API has been promoted to V1, which is pretty interesting. That certificate that relates to the in-cluster CA that Kubernetes clusters come with at this point, and that internal CA is actually used typically to handle issuing certificates for things that are scoped within the cluster itself. So things like the kubelets client certificate and those sorts of things. But it can be used for any number of other things. It's a totally valid certificate authority. It's just scoped specifically within the cluster. So lots of interesting stuff happening there. The kubelets cloud provider and cloud config options are now deprecated, which will be interesting. From the feature perspective, we got a new extension point post filter and the scheduler framework. Lots of work happening on the scheduler lately, which is really exciting. We have the privilege flag to kubekettle run. This one I remember like creating some stir on Twitter about this. And what's interesting about this one is it basically allows us to define a kubekettle run command and then pass privilege, and it will bundle in the command necessary to give that pod all of the privilege or capabilities that it could possibly have. Like it's the most privileged set. It basically makes it so that the pod itself is running as a highly privileged process within the Linux machine that is represented by your kubelet. And so it can do things like have direct access to all the devices made available on that node. It could do things like make a reboot call. It could do all kinds of interesting things when you're in -- privilege mode. And it's put there, I think, mainly for convenience. If you're interested in that issue or what that's all about, definitely go check that one out. Got some bugs and regressions that have been cropped up. Fix XCD immersion migration script in the SCD image. fixing huge page sizes, describe output, some minor fixes. This is an exciting one. I've been waiting for this one to happen for a little bit. This is add retries for KubeADM join. So if KubeADM join doesn't succeed the first time, usually it would just fail and you would manually have to rejoin. This one is actually putting in a retry loop, which is pretty exciting. We are still doing some learning around the newer managed fields capability within Kubernetes 1.18, and so we're still seeing some things crop up inside of the managed fields arena. So yeah, keep your eye on those release notes as they come if you're interested in digging into what's happening with 1.19. There was also a CVE, and this one is actually kind of a really interesting one. My friend Rory also explored this one. Rory McCune, he might actually be with us, although I don't see him in the chat. Going back to the chat, we got Vivian saying hello. We got Mona from Germany. We got AJ from saying happy birthday, Brian. Where did I miss a birthday? Oh, Brian Lyles. Yes. Happy birthday to Brian Lyles. Absolutely. And that's a good reminder. This month seems to be the month for amazing people. Like, I know that every month is a month for amazing people, but it's kind of been surprising to me how many people I have such admiration for or respect for have a birthday in July. It's kind of sneaking up on me a little bit, you know. We got Brian Lyles, Ian Coldwater. There are quite a few others that are all July folks, and that was kind of surprising to me. So always good to see those folks out there celebrating their birthdays and getting noticed and appreciated for, you know, the work that they do, even if it's just once a year. Probably should be more often than that, but you know, it's pretty awesome. So back to the CVE. The CVE is a really interesting one because it effectively kind of breaks the way that we think about the security boundary of localhost, right? So typically, when we think about accessing localhost 127.0.0.1, we think that if we're accessing that IP address, that traffic by law cannot be going to couldn't possibly go to another node, right? I mean, if you're addressing localhost, shouldn't that be kind of localhost? Shouldn't that be right there on the same node with you and associated with your loopback device? So as it turns out, you can configure Linux to do all kinds of wacky things. And in this particular case, what's being highlighted is that with a particular sysctl flag, you can tell Linux to allow for routing that localhost network. And because of that, and because of the way that IP tables works as it relates to kubeproxy, you can do a thing where you effectively NAT out localhost IP addresses and send that traffic to one of the adjacent nodes, allowing you to access services on another node by accessing the localhost IP, which is a lot to understand, but that is a crazy cool hack in my humble opinion. But it has been fixed, or has been mitigated, I should say. And understand that this particular risk is even more interesting because it's not just those system daemons that listen that Kubernetes places. It's also any system daemon that listens to all interfaces on any node would suddenly be accessible. Actually, any system daemon that listens on localhost on some other node would be accessible from the attacking node and configured in this way, which is really pretty interesting. So definitely check this out if you're interested in kind of really fun, trippy network hacks and that sort of thing. This is a fascinating discovery and a fascinating hack. So kind of a fun one. That one was like really fun to play with and look into and stuff. So from the Thank a KubeADM Maintainer department, Emmanuel Evans talks about how he set up a minimal viable Kubernetes. I think this is like Kubernetes the hard way take two, but I really like the kind of test-driven development sort of way that it explores this, right? And so they take a big picture view of how this works, and then they break down the different components: kubelet, kube API server, kube controller, runtime, Docker in this case. And then they go through component by component and take a look at what it takes to set these things up, right? And get these things working. And so it's really kind of a good reminder of the basics of where we've come. With things like KubeADM, we've come quite a ways, right? With a lot of the tooling around things like Cluster API, we've really automated much of this pain away. But it's been really, I thought this article was really a good reminder of the basics or the premise on which we're operating. You can see stuff like this, right, where they take the kubelet command and they run -h and they see 284 lines of output from just the help output of kubelet, right? There's a lot of data. And you can imagine that, like, parsing that into something that is a reasonable configuration of the kubelet is not trivial. So it's kind of it's a great reminder of where we've been and how we got to where we are. Mr. Steve Wade checking in. Good to see you. And Christoph, from Dusseldorf, Germany. And we got AJ. Shouting out to Ian and Brian. We got Steve saying hello to everybody. Good to see you all. I should actually shout out the Atlanta meetup. Somebody want to give me a link to that Atlanta meetup again? Because I think there's another great set of talks coming up. The Atlanta Kubernetes meetup has gone to kind of a virtual state where they're actually accepting talks from people all over the place and presenting them virtually. So that's a tremendous way of handling this coronavirus sort of situation. And if you're interested in, kind of checking out like the Atlanta Kubernetes meetup, you should definitely check that out. I'm sure they aren't the only ones doing it, but it is really great to see that happening. So I'll look up a link for that one here in a little bit, or unless somebody else wants to put it in here. I think Steve there we go. Yeah. Thank you, George. So if you want to check that one out, definitely check that out. I know of a number of people who are going to be talking about that real soon, or talking at that real soon, and it seems like a really exciting way of kind of staying in touch with the Kubernetes community, which is greater than Atlanta, greater than California, greater than everybody. It's all of you, and it's everywhere. It's amazing. So Porter is a new one on me. I haven't actually explored this one. This is from KubeSphere. Porter is an open source load balancer designed for bare metal Kubernetes clusters. It's implemented by a physical switch and uses BGP and ECMP to achieve best performance. This is interesting. I imagine this has some overlap with Metal LB, especially because that's kind of the pocket that Metal LB fits into. You have a controller and an agent. The controller is responsible for synchronizing BGP routes with the physical switch. Then you have an extended IP service in which you can associate an EIP with a particular service. More interesting networking stuff. So this is actually neat. ECMP is really a cool way to handle the Kubernetes load balancer implementation. And the reason I say that's so cool is because if you think about the way ECMP stands for equal cost multipath, right? And if you're on a network and you're routing back and forth between different components, if the cost of sending traffic to two endpoints is equivalent, right, the same cost, then you can easily balance that traffic across the two endpoints. And what that means is that, convergence happens really fast because you're basically always kind of switching back and you're kind of always randomly sending a new connection to one of the healthy endpoints that are the next hop, and you're going to maintain a connection state, right? So if you've actually already sent the first packet of one particular connection to a router, you're going to maintain that state for the rest of the packets associated with that flow. This is just about distributing new connections across the existing routers. ECMP gives us that capability, and it also gives us the ability, leveraging a technology like BGP, to grow or shrink or mitigate the number of routers or healthy endpoints that can attract a particular type of traffic or the next hop of a traffic. And so if you're interested in that kind of technology, if you're interested in networking and how all of these pieces work, this is probably a pretty decent write-up to get started with. I definitely also recommend looking into Metal LB by Dave Anderson. He has done an amazing job of describing kind of the thought behind the design, what he did there, and what has happened inside of that space. So both of these are really great projects. And actually, I think there's a third that I'm familiar with, which is put out by a good friend, Dan Finnerman. It's called KubeVip, which is yet another implementation of this, right? It's kind of interesting. The reason that people build these things, right, is because, like, if you think about it, it actually says it right there in the line, right? Porter is a bare metal load balancer for Kubernetes. And the reason that's important is because, like, for load balancing, for service type load balancer to work within Kubernetes, right, you usually have to have some external entity that you're interacting with to configure and make available that load balancer. In AWS, if you have the AWS cloud provider integration happening, when you create a load balancer, you're going to get an ELB or an NLB, depending on how you configure it. If you're in Azure, you're going to get a load balancer. If you're in GCP, any of these cloud providers actually support it. Same thing with vSphere. But bare metal typically does not, right? So where bare metal fits in is like, well, how can we provide that same capability? How can we define a service of type load balancer and have it populate when we don't necessarily have a cloud provider integration or that external entity to talk to, right? And so this is some of the interesting work happening in that space. Mr. Steve Wade put an article up around reducing flux permissions, and this was, I think, prompted by another friend, Brad Giesman, who was looking into, or was kind of starting a review of Flux as a technology and found kind of some interesting permissions challenges. And so I think that Steve put up, and I think Steve did this before Brad did his introspection, but we were chatting about it online. And this is kind of understanding like what Flux needs access to and how to properly secure it such that you're not giving away complete access to your cluster to Flux when you're using it, right? Which is a, responsible use. It's like following the principle of least privilege. It's very, very important stuff. Oh, and this was in collaboration with the Flux team. Very cool. Yeah, that's right. I did do a blog post on Maui Lion, although that's a little out of date. I need to kind of reassess it. I haven't dug into what the difference between Porter and Metal LB is, but they do look like they try and scratch the same itch. I know that Metal LB is a little more flexible than that. It's not just about BGP and ECMP with Metal LB. You can also implement that as layer 2, which is actually very exciting, right? So which interface will ARP out for the shared IP address rather than being able to attract that traffic using a routing mechanism down to any number of nodes. So very different implementations, but definitely check those out. And in my blog post, I used the L2 mechanism because I was doing it inside of Kind. And so kind of a fun one to look into. Thanks, Steve. I didn't realize that this was in collaboration with the Flux team. So yeah, there you go. Michael Bridgen and Stefan Prodan from Weaveworks. All three of them went down a journey to figure out how to lock Flux down. So exciting stuff. It's good to see those sorts of improvements. Community-driven improvements are almost always like exciting to me. Great to see it. You love to see it, right? Is that what they've been saying lately? You love to see it. This is another one by Steve, and I think this is actually one I've seen before. In this case, it's how SSO brought a cluster to its knees. And if you're interested in this one, definitely check it out. And if you have articles that you've written or anything else that you've actually put out there in the open source community that you'd like me to cover or talk about here in this on sessions like this, definitely check out tgik.io/live before the show and add those links. And I'm happy to dig into it and kind of boost the signal for anybody in the community. So this was an interesting one because it actually highlights a challenge that Dex has. But it highlights it in a way that is actually more specific to some of the other tooling that happens in this space, right? So in this case, Flux reconciles the state of the whole cluster, all of the resources within the cluster. And because of that, it's basically it's making a bunch of calls against etcd to handle all of the tokens that have ever been generated by Dex. Because these are stored as resources inside of Kubernetes. You could access them via the kubectl API. And so that load basically increased the amount of load on the backend storage on etcd, and it did nothing to decrease the real challenge that it was causing it to fall over, right? So very exciting stuff. If you're if you're using DEX, this is definitely one of the challenges of DEX. And I remember this coming up while we were at CoreOS, and I felt like we did some things to address it, but I don't think that it was completely addressed. But yeah, now DEX is actually starting to get some fresh eyes and some fresh efforts on it. Perhaps this is one of those things that we can actually resolve. I'm not sure if this has actually been addressed. If you have an issue that you're tracking with DEX, but if you do, throw up a link. It'd be really great to see that associated with a particular issue inside of the DEX IDP repository. My only feedback on this one is I like using etcd as a DEX backend, but I'm not sure a Helm chart's the right way to do it. I mean, I know that none of that is persistent data, but at the same time, I'm worried that a Helm chart doesn't really have any reconciliation loop to ensure that that etcd cluster is continuously healthy over time. And so I'm a little worried that maybe that'll cause you trouble. Because you can't just like add another etcd node. You actually have to have, there are commands that you have to run to join that new etcd node to the cluster, and commands you have to run to remove an old etcd node from the cluster. So this is the only concern I had when I read this article, but I forgot to tell Steve that out of band. But yes, k8s.af would be a great place for this. All right, back to our wonderful DNS exploration. Talked about that one, talked about that one, talked about that one. Okay. Let's dig into it. So last time we talked about a whole bunch of different things. And this time I want to start off by playing with the configuration of core DNS within your cluster. So before we can do that, oh, I have a cluster up, good. Find get nodes -oy kubectl. All right, cool. All right, so I have a cluster up. That's good. And now we're going to play with modifying the configuration of core DNS directly. And we're going to introduce a bunch of different ideas, and I want to talk about them real quick, and then we're going to get back in, and then we're going to get back into the technical stuff. So the thing I want to highlight here before we get into it is that it's kind of one of those really important things about the a set of assumptions that people make when with regard to DNS. And we talked a little bit about this when we talked about the etc NSS switch file, right? In that, you know, the way NSS switch is configured, it's typically going to look for files or your etc hosts file and try to resolve things there. And then it will interact with the libresolver and figure out if it can interact, if it can resolve it after files with a resolver. And it will take the configuration of etcresolve.conf as the way that it goes about using that libresolver to figure out like what the IP address is associated with a particular name. Now, one of the things I wanted to highlight here is a set of assumptions that I've seen happen over and over and over again and throughout my career, and it always surprises me. And I don't want any of you to ever do this, which is that some people think that you can take that the resolver line, right, inside of your etcresolve.conf, that you can have multiple resolvers in there, and that's true, but it is critically important that each of the resolvers in your resolve.conf have the same view of the world. Okay? You can't, for example, have a resolver that is a local DNS server that resolves specific hosts and put that resolver into your etcresolve.conf and expect that queries that are trying to resolve a host name to an IP address are gonna just try each resolver until they get an answer. That's typically not how it works, right? If one resolver comes back with NX domain, we stop asking because we assume that each of the resolvers in your resolve.conf has a shared view of the world. They all agree that all of the hosts that they're going to interact with, that entire host list that make up, you know, the upstream configuration and any specific configuration is specific to the, is consistent across each of the resolvers inside of your etcresolve.conf. So watch out for that one, because I have definitely been bitten by that one myself, and it's one of those ones that comes up over and over and over again, right? Like people say, well, I've configured a DNS server with these hosts, and I want to be able to query that, and so I just added it to my resolve.conf, and it's not working, and I want to understand why, and here's how we're going to get into this, and this is going to be where we introduce the idea of stub DNS and modified upstreams and those sorts of things, and we're going to play with this idea of like split horizon and those sorts of things and how they work. So, back to screen and face. Let's get into it. I hope that was helpful and that y'all understand what I was talking about. But if you don't, please feel free to ask me questions, because that's a topic that I've run into a number of times, and I hope that I've captured it in a reasonably easy to consume way. So just let me know. And you're right, it just doesn't work. All right. Exactly. Yeah. So, moving on here. The order is important. It depends. It actually really depends, Waleed, on the implementation on your host. Like if you're using systemd, resolve.conf, it actually tries to be a little smarter about it, and it'll try and actually remove resolvers that aren't responding, but it can really only understand that based on whether the resolver is responsive on that consistent set of queries or not, right? So yeah, it really kind of depends on your particular resolver. Not every resolver does it the same way. It also depends on how you've got your resolver configured, right? Like in many cases, people will use like a local DNS cache or a caching name server on their host, as in system resolve D, and then that will actually handle kind of the more intelligent way of checking things. So, this is a file that I have a link to. Actually, before we do this, we'll get to that one later. Let's do that one over here. Okay. So in this link where it says stub DNS so cool, into the docs link in our notes today is where this link is going to be located, and it refers to customizing the DNS service, and we're going to play with this a little bit. Now, to kind of set things up, what I've done is I've created another zone inside of my Route 53 area in AWS, and I'm not associated it with the root domain itself, right? I've created tgik.k8s.work, and if I do a search for that today, just in the public internet, right, tgik.k8s.work, I'm going to see it doesn't have any records. There's no NS records, dig, NS, there's nothing, right? And that's because I haven't made it public. I haven't exposed that particular set of name records to anything else in the system. I've just defined it inside of AWS. So I've created a new domain, tgik.k8s.work, and AWS gave me some name servers that are going to announce the configuration that is made up of this zone file. But I haven't actually pointed anything public at these name servers as of yet. And so today, it's kind of an isolated domain name service that nobody knows about in the world, and we're going to play with that a little bit. Yeah, it does kind of pick one randomly in most cases, but really is kind of it is kind of changed, right? So like glibc and muscle handle this differently from each other, right? And that's what I mean is like it really depends on your implementation, both of the resolver and also of the host. So if that's a thing that you want to dig into, it's definitely a behavior that one should understand and experiment on. So here's our domain. We've got tgik.k8s.work. Let's go ahead and play with this just a little bit before we get started here. Oop, that's not what I wanted. So I do dig ns tgik.k8s.work. I'm going to send that traffic at this little fella here, which is one of our name servers. So if I go ahead and query for NS or for the name servers for this particular domain against one of the name servers, then it will tell me about all the rest of the name servers. And that makes sense, right? And I can also dig test.tgik.io against that particular name server. In this case, I'm querying the name server after @ so I'm querying one of the name servers that is known, NS1378 AWS DNS 44.org. And I can see that if I query that, I can see that I'm getting a response back, and the response is 4.4.4.4. Which is in line with the configuration that we saw over here. Aha! Specifically this line right here, which is a really fascinating record that you can do in most DNS implementations, where I have what's called a fall-through hostname here, right? So what I've done is I've said anything not more specifically defined resolved to 4.4.4.4, and anything more specifically defined resolved to whatever it is, right? It doesn't matter where in the order this record exists, but what this is referred to, because it's a wildcard, sometimes we think of it as a fall-through record, right? Like if somebody tries to come to tgik.kh.work, and I don't have a host name or a CNAME or anything else recorded for that particular entity, or for the A name really, then it'll go ahead and get kicked to that result. And so kind of an interesting fall through idea. But let's go ahead and look up testing, and we see the result 8.8.8.8, right? So testing gave me 8.8.8, but pretty much anything else, right? Let's see, Lamati, for example. Lamati is 4.4.4.4 because of the way wildcard DNS works. So I've got a wildcard record in DNS, and anything I don't more specifically configure will be sent to that DNS, to that resolution. Kind of neat. So I set this up because I wanted to play with stub routing inside of the core DNS configuration, and we're going to play with that a little bit more and see how that might work and why that's kind of an interesting use case within Kubernetes. This is the configuration of core DNS. So let's start with the config map that is known inside of our cluster already, right? And so I'm going to do octant. Click over here to octant. And take a look at our config maps in the kube system namespace. Take a look at core DNS. And here we have the default configuration of core DNS inside of the cluster, right? We have a Prometheus port that it's exposing on port 9153, and we're also exposing port 53. And this piece right here, I think we talked about this a little bit last time, but this piece right here basically is telling is configuring core DNS to forward its resolver to the file etcresolve.conf. So however etcresolve.conf is configured, I want my core DNS pod to use that file to figure out who the next upstream is to go and query, right? And so when I, inside of a pod, make a query of my DNS server within the cluster, which as you recall might be the service cider plus 10, right? So if I'm doing a query against, in my case, 1096.0.10, that query will come to the core DNS pod. The core DNS pod will determine, hey, do I have an answer for that? Is that answer part of the cluster.local domain? Is it associated with the Kubernetes plugin within core DNS? Like, are you asking me what kubernetes.default.service.cluster.local is? Or is it something I don't know about at all? And if it's something I don't know about at all, then I have to go ask my upstream resolvers to give me an answer, right? And in this configuration, the upstream resolvers are all known inside of etcresolve.conf. And this way, this is the default configuration. It doesn't get super creative. And if we look at the way that works on the pod level, we can actually even, and I know that we covered this in the last episode, but just real quickly, what we can tell from the configuration of the pod down here in the DNS policy piece, right? Because a DNS policy uses the default DNS policy rather than, I know it's a, I'm gonna make this point again. It's a terrible name for a policy, but in this case, DNS policy default, which is not the actual default for DNS policy. The default DNS policy is cluster first, right? It basically uses the configuration presented by the kubelet. But if you configure the DNS policy to be the keyword default instead of cluster, then what you get is a view of the resolve.conf as the kubelet sees it, right? So typically, the kubelet will be smart enough to look to make sure that the resolve.conf that the core DNS pod sees is one that includes the name servers that the node itself was handed. Even if you're using systemd, which is really cool. So like even if you're using systemd resolved locally, the kubelet's actually smart enough to go, oh wait, I can't hand you a resolve.conf that includes 127.0.0.1. You're not in the host network namespace. I need to make sure that I hand you a resolve.conf that makes sense to you. And so kubeadm handles this. I think the kubelet is actually pretty smart about it. There are flags in the kubelet where if you want to customize what that resolve.conf is and point it at a different file, you can also do that. So there's lots of intelligence we've built into the system over time that allows us to ensure that when core DNS comes up, it comes up with a reasonable view of name servers as known by the underlying node. All right. Moving on here. So let's go ahead and play with this configuration. And we're gonna first play with it a little bit by changing the upstream resolvers. Instead of using resolve.conf, we're going to go ahead and configure. We're going to change the configuration to use like 8.8.8.8. So the way that we can do that, don't believe. We can go ahead and pop open our editor. And we're just going to go ahead and dynamically update the configuration here inside of this piece here, right? And so I'm going to forward all queries to 8.8.8.8 or 1.1.1.1. Let's go ahead and start up our example pod again, like we did before. We'll do apk update. Looks like DNS is still resolving again. If I do my cat etsy-resolve.conf, I can see the DNS configured again, just like using 10.96.0.10. That works the way it did before. And if we do dig, actually, apk add bind utils, is that it? What it was? APK search bind. Y'all might remember. Bind tools. Is that what it is? Bind tools. Okay. APK add bind tools. Okay. Dig google.com. And we can see that we're still getting a resolution and that our resolver was 10.96.0.10. And again, we see that behavior of core DNS, right? It's only going to hold a record for 30 seconds. But we are seeing that the clocks are different, and they're different because we have multiple resolvers behind that service, right? And so that is how, and this we covered a little bit in that first episode. Because we have multiple core DNS pods, the clock here that describes like how long this record is valid for is actually going to be represented differently depending on which of the core DNS pods we reached directly. So talked about that a little bit in the previous episode. If y'all are signing in to your very first TGI right now, go check out that other episode first, right? And then come back, or just hang with us and learn stuff and then come back later. Either way, but you're definitely gonna want to understand what's happening in that other space as well. All right. So what we've done is we've gone ahead and changed the upstream servers. Now, the reason that this would be valuable, the use case for wanting to change your upstream servers inside of all of Kubernetes, which is what we just did, right? We just changed our resolvers from that node resolver to a public resolver, 1.1.1 or 8.8.8. And the reason that might be valid is because, and there are a couple of good reasons for this. If we change the upstream resolver to use our corporate DNS, for example, or a set of DNS servers that are specifically set aside for handling the load of DNS queries from infrastructure within a particular zone, then this allows us to basically make it so that the upstream resolvers are going to be, designed for that particular purpose. And that allows us to further ensure that, we're designing these things for the sort of resilience that is necessary. One of the use cases, and I'm going to call this one out now, and we're probably going to talk about it a couple more times, that comes up in this particular case a few times, pretty frequently, is things like this. And let me show you this one. This is actually kind of a mind-blowing thing for me when I first discovered it. DNS query limit. So I need more water here. Hold on. This doesn't seem like a lot of queries. Or sorry, this doesn't seem like a low number. 1024 packets per second. But this limit means that a given EC2 instance over a given ENI interface can make 1024 packets per second of DNS queries, and then after that, the DNS servers reject the traffic that exceeds this limit, and that can cause. That's a good point. I should use the DNS utils image, and that can cause some real havoc in the way that DNS resolution works. And this is a limit in AWS, and I imagine that other clouds also have the same limit. But let's just think about it a little bit from the perspective of a Kubernetes cluster and how a Kubernetes cluster operates, and kind of piece together how this might be a problem, right? And so within a Kubernetes cluster, we have a couple of control plane nodes, and then we have maybe 100 or so worker nodes. And by default, the way this configuration system works, there might be 2 core DNS pods. And those 2 core DNS pods might even land on just one of our control plane nodes, or just one of the worker nodes. Both of them could land on the same node. If that happens, then that means that all of the upstream requests, all of those upstream DNS requests, are going to be coming out that ENI interface toward AWS name servers by default. And if you think about the number of DNS queries that are just make up a single connection to a database, right? Especially as you consider behavior like we talked about last time with musl versus libc, where we basically make a query for every iteration of the DNS name, right? So if we say we're going to resolve google.com, right? And so the way that google.com is resolved by core DNS is you're going to try and resolve google.com.cluster.local.cluster.local.service.namespace.cluster.local. You're going to make all of these queries with just google.com because the system is going to assume, because of that ndots configuration, that unless you actually provided a string that specifies that this is a fully qualified thing by appending a dot at the end of your host name, it's going to assume you used a short name, and it's going to try and resolve that short name against the configuration that it knows inside of your resolve.conf. Right? So it's going to take each entity inside of your search path, append it to the short name that you've given it, even if you didn't give it a short name, and try and resolve that first. Now, all of that traffic dies right there at core DNS. It doesn't get forwarded to upstream. But any other traffic that comes through, right, that might be considered a short name, would go against upstream eventually, right? And that throttling causes all kinds of wacky things inside of your DNS configuration. So we have two core DNS pods. They happen to land on the same node. That means that we have a single ENI interface into the VPC. We're limited at 1024 packets per second. This can be a production outage. This is the makings of a production outage within Kubernetes, right? And there are lots of things we can do to address this, right? We can make sure that, for example, that we have more core DNS pods, and we can ensure that those core DNS pods are spread across control plane nodes or across different sets of nodes to ensure that we're not like stuck under one. And then the other thing we do is we can configure it in such a way that the upstream resolvers are not the AWS resolvers. They're resolvers that we have configured for our infrastructure, right? Maybe use a resolver that you have configured. And that way it gives you two pieces of control. It allows you to extend that resolver to handle things like split horizon. Like you might have a set of resolvers within your corporate network that you want to use because they understand how to resolve services that are made available in a different region or inside of your infrastructure connected via a VPN into your cloud infrastructure, right? And so if you set those upstream resolvers, then they're going to be able to provide you the flexibility of defining what host records are, and they're going to overcome this particular limitation by not limiting you when you hit the edge of traffic. The other piece that's neat about this, about setting upstream resolvers, is that you don't have to do it wholesale, which is really kind of neat. And that's what we're going to talk about next, right? We're going to talk about stub DNS and dig into it a little bit there. So here's the cool part, and I really dig this. So we have this forward line here, right? And that forward line basically gives us the ability to set our upstream resolvers. This forward line basically sets forward anything not resolved by a plugin elsewhere in the configuration to whatever the upstream names are, right? And so in this case, it's pointing it at 117.16.0.1. In many cases, it'll point it at whatever. I think it's like preferred, but not required. So for example, in my configuration, sorry, Marcos, I was answering your question. And it's a great question. Let's just investigate that real quick, and then we'll come back to this part. The question is, are there anti-affinity configurations in the default deployment of core DNS? I believe there is some effort of that. kubectl get deployment /n system. So it's being told to tolerate the effect of node role master, but the node selector in the configuration system just says it has to land on a Linux host. It doesn't actually say that it has to land on a particular type or role of host. And further, there's nothing in this configuration that allows for affinity or anti-affinity. So by default, no. The answer is it does not. In fact, it's actually a little bit more permissive than many, because in this case, it's actually it's tolerating the no schedule effect on the role master, and that means that even if the master nodes are tainted, then core DNS could still pick that to deploy to, right? And the node selector, any node that matches Linux is going to match. And now if you think about it, this is a little bit of a race. And this is one of the challenges that we have, right? In this configuration, it's a little bit of a race. Like say we're bringing up a cluster. We're going to start with like the 3 control plane nodes. And we're going to bring up the worker nodes after that. When we get to the state where we deploy core DNS, that core DNS deployment will land on whatever nodes are registered with the Kubernetes cluster at that time. So normally what I see in instantiating a cluster is that we see core DNS attracted to the control plane nodes almost by default. All right. So there's that. Now, back to our configuration. I want to play with this idea because this will be a fun one to dig into also, right? So we got our forward configuration. Now we're going to play with this idea of stub routing. Now earlier I said one does not simply throw another resolver into their resolve.conf if they want to pick up things like these other host names, right? So for example, if I jump into my configuration, I do docker run, actually, clear. Let's go back to our bash here. So here's my default resolve.conf, right? And if I do apk add bind tools, I think the reason I don't use the DNS resolver one is because actually I have to remember that path, and here I only have to remember the word bash. Makes it much easier for me when I'm playing around with these sorts of things, right? So if I do dig testing.k8.work, or actually it's tgik.k8.work, I don't see anything resolving, right? And that's fine. We know that that's not going to resolve. There is a resolver for the root domain, because it is a domain I own, but I don't have anything informing the root domain how to delegate a query for the TGIK subdomain down to that other set of resolvers. And so, let's go ahead and do the thing I tell people never to do and explore why it's such a fascinating topic, right? So, oh, shoot. AWS login. Default. I'm using AWS Vault to handle my credential stuff, which is like one of my favorite tools for this sort of thing. I'm probably not going to explore it in this episode, but if you're interested in understanding more about it, definitely go check it out. Very, very cool stuff. So here's our name server, our resolver, right? And we know that it works because we were using our dig commands earlier. I'm going to go ahead and copy that one. I'm going to come over here to my resolve.conf. apk add nano. Actually, vim. Made you look. So vim etcresolve.conf. And I'm going to set another name server. Name server. I wonder if that would actually work. Yeah. Go ahead and put the IP address in there. All right. So I've set my resolvers. Now I have two different resolvers, right? At etcresolve.conf. I've got my 1096.0.10, which is my DNS for the cluster. And then I also have this other name server, which is the resolver for the host. And I know that they both work, right? But if I do dig testing.tgik.k8.work, I don't get any resolve. I don't get any result, right? In fact, I got an NX domain, but I know that one of my name servers in here knows how to resolve that, right? Like I can query this guy directly. I can do dig, I can do the same thing and just point at that resolver. I got a record. Why am I getting an NX domain, right? And this is exactly what we're talking about by the challenge, right? You can't just add another name server that knows things that the other name server doesn't know to your resolve.conf and expect things to work normally, because they won't, right? You'll get weird behavior, like, you know, you might get lucky and it might try to resolve that record against the correct name server, and then you'd be good for like at least a few, you know, in this case, you'd be good for 300 seconds, maybe, right? Totally wild. But yeah, don't do that, because it creates problems that you're going to tell stories about for the rest of your career when you do it. All right. So, but if we legit did want to do it, how could we go about it, right? kubectl edit config map -n kube system core DNS. Let's go back to our configuration example here. And we're going to go ahead and pull this configuration out and copy it over here. Oh, bummer. I don't still have it. Nope. Interesting. Well, I mean, it's all still here anyway. So we're going to set core DNS to forward to make sure this gets parsed correctly, because it does seem kind of weird. So let's jump back into our bash pod here. Cat seresolve.conf, dig google.conf. Oh, apk add bind tools. All right, so we still have a resolution for google.com. But what about testing.tgik.k8.work? There we go. That's neat. Waiting for things to converge here. There we go. Now we're all converged. All right. So now our core DNS pods have all converged, and now they know this record. And if I look up tests, I don't see any timeouts like I did before, right? Because now each of the core DNS pods has been configured with that upstream resolver for that domain, and we're good to go. Right? And so I can do Lamati like I did before. Oh, sorry, my bad. Right? And I can still see the resolution happening dynamically, quickly. It's holding that record for 30 seconds. And that way we know it's core DNS doing it. And in this way, this is actually a really fun part. we've configured our system in such a way that if you're using the default configuration of the DNS policy for your pod, you can now rely on that subdomain to resolve records that are known only to it, right? We basically kind of added a stub DNS domain, and now we've actually got a reasonable implementation here in such a way that we can be relatively assured that if we wanted to handle a specific case, and in my case, like say my enterprise was TGIK.K8.work, and I wanted to be able to make sure that I could resolve names for that, what I'm doing in this configuration here, oh, it's fixed. So what I'm doing in this configuration here is I'm saying that if the query is headed for TGIK.K8.work, if that matches the domain, the subdomain for that particular record, right? So when the query comes in, and I have that particular record coming in, I want to make sure that I forward that request to this name server, or to one of the name servers in this list, right? You can specify multiple name servers. You don't have to actually only specify one. And so the killer part about that is now I'm making like 3 decisions, right? My first decision is this record something that is associated with the Kubernetes plugin, right? Is this Kubernetes.default.service.cluster.local or service.default.cluster.local? And if it is, then answer it, right? If I don't know the answer, then I'm going to go ahead and forward it to 1.1.1.1. And I'm going to cache the result of that for 30 seconds. And then down below, I have specified a subdomain. I've said, but if the query is going to anything.tgik.k8.work, then go ahead and forward that request differently. Handle that traffic differently. Forward the request for that domain to 205.251.197.98. Which gives us the ability to get really creative about the way that DNS resolution works within pods. This is not going to overload core DNS. Yeah, split DNS config for security maybe. Like, I don't necessarily need people to know about testing.tgik.k8.work, right? Like, it's not a public record. It's usually only used for my own internal infrastructure world, right? It's not used for my public facing. And so I want to make sure it is specified globally, but only for that particular pod. But the way this is configured, I can make it so that if I had a particular domain that had host records that were infrastructure specific, and many enterprises you'll find have this sort of a domain, right? It'll be like dev.myenterprise.com, right? Maybe that's not a public facing domain for good reasons, right? It basically just it slightly increases your attack surface, nothing super serious, but in some ways it could be an information leak. This way I can make it so that only those pods that are using the default DNS configuration within Kubernetes can actually still resolve that stuff, right? And when that I think it actually provides a cool configuration for how that stuff works. What else can we do? So, Maddie, the answer to your question is that Prometheus port is exposed on a kind of a system level, right? So on the port, on the pod itself, it's exposing metrics that it knows about. I guess your question is like, can we determine if their query is going to that sub DNS resolver? Is that where you're trying to head? That's a good question, if it is. But let me know if that's where you were headed. And actually, you know what? Let's try this out. So, kubectl get svc -n kube system. Cool. -o YAML metrics. I mean, you do, right? I don't think you need another Prometheus configuration, because you're telling Prometheus, you're instrumenting the core DNS domain. You're instrumenting the core DNS application, not necessarily that particular subdomain. But let's take a look at what the metrics look like, and then we'll know if I'm talking about the right thing here or not, right? So curl 1096 metrics. So here are the metrics that are exposed by core DNS. And let's just grab the ones that start with, begins with hash. Cache hits and misses. I think I wonder if it's actually just counting it as a forward, or if you're looking to distinguish the type of forward that it is. That is an interesting question. Does the core DNS pod sync the cache, or is each one managing its own cache? Each one manages its own cache. I've always added one Prometheus line per stub to get metrics for that. So, yeah, that might be right. You might be totally right about that. And I'm kind of surprised by that. I thought it was actually being instrumented individually, but specifically. So if we do make that change, that's a very good point, Maddie. Would you add what would that look like, Maddie? Would you add just the line Prometheus below it, or would you like specify the port? Probably don't want to specify the port. So Maddie, when you configure this, I'm curious, like I've not configured this particular thing before. When you're configuring the Prometheus piece for the stub, do you specify that part do you have to specify a different port? Googling, it seems you can specify the Prometheus directive on the same port for multiple stubs. All right, let's take a look. So was this before? Was this here before? That's a good question. So this is the IP address of the upstream resolver for that particular set. We got no error from there. So weirdly, I would have thought that that would have been a global configuration. So I'm learning something here today too. It's actually kind of a neat one. So if I drop that Prometheus line from the second piece, then in theory, I shouldn't see 197.98 in the metrics anymore. But I do continue to see it there. See, I thought that Prometheus would be evaluating that because it was a global Prometheus configuration. That's interesting. I have to look into that. What's interesting about that is that, like, you're making the assumption that because I defined another block, that Core DNS, the application, would instrument that separately. And I'm making the assumption that because Prometheus is configured as an instrumentation of Core DNS as an application, that any call that it makes that would be instrumented consistently regardless of the block that it associates with. Yeah, that's a good point. All right, so we removed the Prometheus piece, so let's do kubectl delete pods-n kube system -l case app equals kubedns. Like dsutil flush, right? Is that how it goes? Aha. Dig testing.k8.work tgik.k8.work at 1096.010. And let's look up. Ag. All right. So even though I don't have the configuration set to look for that particular resolver, I still see it instrumenting the calls to that particular resolver. Right? I've sent one forward request to that resolver based on the configuration. So I think it's app level. That's an interesting one. All right, let's keep moving though, because I don't want to get bogged down too far. Anyway, we have talked about the way this works, and how that works, and how it's configurable, and so that's all pretty cool stuff. Let's go ahead. We talked about that one. All right, so let's explore this one, and then we're going to get into service discovery things, and we're going to get into external name, and then we're going to do node local DNS. So we got a little bit left to cover in this episode before we're done. So let's keep moving. All right, so there are other things you can configure inside of, what is this? Why is there a note there? Boop. What? Cancel. All right. There are other things you can configure inside of, via the API inside of Kubernetes. Like you can configure the resolve.conf specifically for a pod. You can configure the dot. You can you can add things to the hosts file for a pod. And you can also do things like configure external name, which probably should be up here also. But let's play with those things real quick. So we talked about customizing DNS. Let's talk about services and names and how those things work, right? And then here we're going to get into kind of like the discovery piece a little bit. So let's just beat that up a little bit. Kubernetes DNS-based service discovery is an interesting implementation of things, and we've explored this a bit within the configuration in the previous episode. But let's go ahead and bring this up again. Okay, add bind tools. So remember that I think we talked a little bit about service discovery last time, but I want to show you a trick that I was kind of mind blown by. When we introduced core DNS as the default cluster DNS, we also, as part of the Kubernetes DNS plugin piece, enabled this really wild wildcard DNS thing, which is really fun. So anything dot cluster dot local. There we go. All right. So what this does, which is truly wild, is that you can use dig or other tools like it to discover services within, I thought it was, maybe it's any rather than anything. There we go. So you can use dig or other tools that can actually look up host names and stuff to discover services that are exposed cluster-wide from anywhere inside the cluster using kind of an interesting incantation of any or any star within the cluster, right? So if I define a new service within the cluster, this will now be discoverable from any pod within the cluster using this mechanism. And this is part of that Kubernetes plugin piece that Core DNS configures for the cluster. It allows us to do service discovery. And this is a really neat one. Like what it does is it allows us to effectively enumerate all the services that are exposed within the cluster across the entire cluster, right? And so if I were to do kubectl create namespace test, kubectl create service. Actually, I got to do deployment test image equals inanimate, actually nginx. So I got my test deployment -n. We'll call that one test. So we've deployed it into two different places. Kubectl expose test1. Deployment test name test1 port equals 80 -n test. So now if we do kubectl get svc -o wide, we can see these are the -a. We can see these are the services that are known about cluster-wide. We've got the Kubernetes default service defined inside the default namespace. We've got test1 that is exposing our test service within the default namespace, and we've got test1 exposing the test deployment inside of the test namespace. And if we jump back into our pod, just like we had before, apk add bind tools, dig srb star.star.svc.cluster.local. Then we see those things pop up, right? And we can see kind of this, I think really helps us understand how we can build, based on that DNS service discovery within the cluster, how we can build or even discover the different services that are available to us within the cluster, right? And so I just created two new ones, test1.test.service.cluster.local in the test namespace. The service is named test1. The namespace it's in is test, and it is a type service. And cluster.local is kind of the default domain. You can configure this when you bring up the cluster. We have our kubedns service that we know about. We have the Kubernetes service that we know about. And then I also created a test1 deployment in the default namespace. And we can see all of those things, and we can discover them using this really kind of a clever serve trick, right? And so just to highlight what's happening here, I'm looking up all the SRV records for literally any service within the cluster. And I thought that there was another incantation of this that would catch pods, but I guess there isn't. So star.star.svc.cluster.local, and you can enumerate all of the services exposed within your cluster. So interesting stuff. You do. Why do you need to expose it though, Maddie? Like, I'm all curious now, because this is actually not something I've ever done. So you need to enable Prometheus metrics per zone, and I'll add a link in the core, to the core DNS doc that describes how this works to the show notes. Also verified this in a test cluster. Because what I see is different. I see it enumerating at least some values, regardless of whether I have that configuration in place or not. And so I wonder what they're enumerating differently that we didn't get in our output. This isn't quite the same as listing endpoints, because what's here is actually just the service IP address of the endpoint, rather than the pod IP addresses themselves, right? So endpoints are representative of the actual backing service. This is actually just being able to. This is more the equivalent of kubectl get service -a for all namespaces in the cluster. I think I remember there being a way to turn it off. I don't remember exactly what that trick was, but from a security perspective, it kind of bothered me also. But it definitely highlights yet another one of those assumptions that makes it very clear that Kubernetes is not a hard multi-tenancy focused solution, right? It's at best used for soft multi-tenancy. So we talked about service discovery things. We talked about the important assumptions about resolve.conf. That was earlier when we were talking about one does not simply add another resolver to resolve.conf. And now we're going to look at these two pieces, which are both pretty neat. Down below here, there are a couple other ways that you can configure the cluster, or you can configure your pods. What they're highlighting here, which is interesting, is that you actually have, obviously, the DNS policies that we've talked about. Default, which is not the default, allows you to see the resolve.conf of the underlying node. Cluster first is the default for the cluster, and it allows you to see things which are known about within the cluster. Cluster first with hostnet. If you're using net equals host inside of your inside of your pod spec, this allows us to configure that resolve.conf so that it still uses the 10.96.0.10 resolver, even in hostnet, which is pretty slick. And then none is the one that we're going to explore next, right? And so if we have configured none, then we can actually define ourselves what we want that to look like. So let's go ahead and play with that idea by go ahead and deploying this. kubectl, run it. Copy. Exit. kubectl, run it. All right, so our manifest that we just deployed inside of our test cluster is this one. And what this is doing is it's setting the DNS policy that we talked about before to none. And then we're passing a DNS configuration. Now, I've talked about this lots and lots of times, but just to highlight, if you want to explore what that pod spec might look like, you can always use kubectl explain pod.spec.dnsconfig. Right. So if you wanted to explore like what you could do inside of this particular space and how they can, and how those, what these entries are for and what they do, you can actually use kubectl explain to explore that stuff, right? And so you can specify a list of name servers, you can specify options, and you can specify different entities for the to append to the search path, and this is represented as a list. Even though it says string, it's still a list. So, in our example configuration, we've specified two searches: ns1 service.cluster.domain.example and my DNS search suffix. And we've configured ndots. If you wanted to customize the configuration of ndots, this is one way you could do it. And we've specified the name servers and all of that stuff, right? So inside of the configuration of our pod now that we brought up with that configuration, if we look at our resolve.conf, we can see exactly as we would expect, right? That list represented in order. So ns1 service.clusterdomain.local. We've got our options configuration, and we've also got our name server. Now, obviously, DNS will be super broken here, right? So if I were to do ping google.com or curl google.com, that would not work at all, right? Because there is no name server 123 as far as I'm aware, and it seems pretty unlikely at the moment. So this is a way within your pod spec, within your deployment, if you wanted to, you could actually configure DNS to be specific to yourself. Now, this is also kind of an interesting security point, Eric, because I feel like this is an interesting one to want to have some admission policy around, right? Like it may be that you want to have control over what DNS record or what DNS servers and the configuration of that DNS servers are going to be used within a multi-tenant cluster, right? And in this case, you're actually allowing for the definition of the pod spec to configure that name resolution rather than assuming that that name resolution will be configured holistically across the cluster. Kind of an interesting point from an operations perspective. So this is one of the ways that we can modify this. Now, this is in the pod configuration. I just brought up a pod. You can absolutely include this change in a deployment, a daemon set, and any other primitive within Kubernetes that creates containers, right? Because we're defining that right here in the spec file. So you could do this with a deployment, daemon set, stateful set, any of those things. The last thing I wanted to point out from the DNS configuration of modifications that you can do to the pod is this piece here, right? So remember that we talked about this before. In NSS switch, typically files are first, and then we go to try and resolve things. Well, knowing that, there are some things that we can do to configure this, right? We can specify a different configuration. So let's go play with that real quick. kubectl apply -f kubectl exec ti oh, they didn't leave it running. So kubectl log /n host alias. Yeah. So in our configuration, what we saw, right? We're actually specifying a couple of host names. We're going to forward foo.local and bar.local to 127.0.0.1. And we're going to, so anything that matches that particular host name is going to go here. And we're also going to do forward foo.remote and bar.remote to 10.123. And we're going to configure that in the etc hosts file. And then inside the container, they basically just ran like a cat etc host to prove that it worked, right? And so we can see that same output here, right? So there is our resolve.conf. So any query to foo.local or foo.remote will be resolved to the IP address that we've configured here, right? Now, what's neat about this, one thing I wanted to, like as a quick funny aside, is that this is not a new trick. This is an example of a hosts file that I know has been in existence forever, right? And in this particular example, basically what they're doing is they're determining the name records of things that should not be resolved within their domain, and then configuring that domain to resolve against localhost or resolve against 127.0.0.1, right? And so this is an example, kind of an extreme example of that, right? Maybe I don't want mediafastclick.net. I don't want my browser traffic to go to that. I want to dead end that traffic, and the way that I could do that is by sending that traffic to localhost, where I don't have anything running on that port, and it will just die, right? Basically breaking the web page loading, but breaking it in a very specific way. Kind of, yeah, Pi-hole does this. Gosh, there's a million examples of this, right? Pi-hole does this kind of more in the way that like Core DNS does, in that you have a DNS resolver, and you're using that DNS resolver, and you can programmatically configure that DNS resolver to say, I don't want to send any of my traffic to these domains that are known based on our community as domains that I don't want to go and interact with, right? So the same trick, but like you could totally, that's what I was calling out here, is like this is an example, kind of a much slighter example of a technique that's been in use forever for doing things like limiting access to things that you don't necessarily want to allow your computer or your application software to go and interact with. So kind of fun. You can do negative and you can also do positive, right? And so in this case, we're doing positive. We're saying like, if you are trying to use this host name, then map it here. If you're using a remote host name, then map it here. And here we're doing like negative. I want to throw this traffic away. I don't want my application to actually connect to this stuff. Kind of neat stuff. So we talked about those two things. Now I want to talk about external name, and then I want to get into node local DNS. And it's already 2:35, but we're going to keep going anyway because I'm crazy like that. Yeah, Pi-hole is really cool. It's a great way of understanding just where your traffic's going, and sometimes you probably don't really want to know. So kubectl create service type, actually external name, and external name will be google.com. We'll call this test 2. So what I've done is I've just used the kubectl create service command to create a service of type external name. And this is part of that, again, that Kubernetes plugin that is running inside of our core DNS pods within the cluster. And what this does is it creates a CNAME, right? And so let's go ahead and jump into our pod again. Do apk add find tools dig any.any.svc cluster.local. Those are all of our services. I wanted SRV there. So in our service output, right, we can see that there is now no A record. But there is, in the output of just looking for A names or C names, we see that there is an A name for CNaming to google.com. And there are multiple A records because we're just matching everything, right? And so if I do dig a CName test2 dot default, then I can see that the result is that CNAME that I just created. This is a type external name. This is how it's implemented. It's implemented as a CNAME, and so any query I send to this will get CNAMEd to google.com, right? So if I do curl google.com wc-l, for example. Oh. Well, let's just do it. -l, yes. Oh, really? apk add curl. So there's the website, and we can do wc-l. We can see there's like ten lines of output, all minified and stuff. And if we use our service, right, this will be test2. We should see a different result, but we're talking about that here in a second. Test2 dot default dot svc dot cluster dot local. Why do we see that result though? That's kind of interesting, isn't it? So we saw that second result because there's no way that Google on its HTTPS protected website is actually including this as a subject alternative name, right? And so instead, when I sent that request, the SAN or the subject alternate name that I tried to query that particular website with didn't match the certificate. And that's why we got that extra line. And it's also why we got that output of like, we failed to verify the legitimacy of that connection. All right. Nah, it still would break, right? Because there's no line there. There's no, I'm not in their SAN list. So even if I added the host header, it would still fail, right? I could fool like some parts of the system, but at the end of the day, like what shows up over there, it's going to be the important part. All right, so we talked about external name. It's basically a way of creating CNAMEs that you can reference internally. The reason that use case is so cool is because then you can do things like, you know, curl test2 and get a response back from your entity, whatever that entity is, right? So if it's in Google, then you'll get a response back from Google. If it's within your infrastructure and you are like, you know, you have like a local MySQL servers or whatever infrastructure that is like specific to a region, and you want to just have an abstract name that you can use within the configuration of your application, right? I need to use some local cache, and I'm going to call that local cache X, and I'm going to define an external name for X so that I can just always refer to that local cache without having to more specifically define it within a particular region. And then in my configuration management system, I can actually say every one of my regions will have X defined for whatever the local result of X is, right? And that way I can use a short name to resolve it. I can assume that the connectivity part of it will be resolved. Now, there's no guarantee that the local cache will be in any way usable across these different regions. That's a different problem. But from a name resolution place, this is what kind of the external service use case is, and it works pretty well. All right, last thing we're going to do is explore node local DNS. Let's go ahead and do that. So we'll do kind delete cluster, kind create cluster, config equals kind. The reason I wanted to recreate it is because I wanted to have more nodes than one, right? Like I'm going to bring up my control plane here, and we're going to have multiple worker nodes. And that's the important part of this particular test because it's node local DNS cache. And so we're going to play with like how it's configured and how it works and all that good stuff. So let's bring that guy up. While we're waiting for that to happen, let's go ahead and go back to our notes. Whoops, I forgot to put the link in for node local cache. Ba-doing. So we talked about the problem of like Route 53 limiting the number of DNS queries we can get away with per second, that kind of thing, right? And this is another way of resolving that, right? So we could solve that. We could approach that problem in a variety of ways. We could increase the number of core DNS pods. We could configure anti-affinity. Or we could do a number of things that would actually allow us to improve the resilience of DNS within our cluster. But one of the other things we could do, just like we do at our host level, is we could put a caching DNS server on each of the nodes. Okay? Now, in a past life, while I was at CoreOS, I actually helped implement this for one of our customers before this feature was in existence. And this was actually kind of a fun one. And what we did was we basically created a deployment, a daemon set of core DNS, and we bound it to, we bound core DNS to the node's IP address, and then we configured the kubelet to pass a resolve.conf that included the node's IP address rather than 10.96.0.10. And that way, when it generated a resolve.conf for the pod, using DNS policy default, actually no, using DNS policy cluster first, it would actually use our the node IP address for the resolver, and that node IP address would be where we terminated core DNS for that particular node's traffic. And so we kind of implemented the same thing, not nearly as well as it's implemented here, but kind of a cool history fact. So this is how we can turn this feature on. This feature can be enabled by using the following steps: prepare a manifest similar to the sample node local DNS YAML and save it as X. So let's go ahead and look at the sample. Raw. So we have a service account being defined. It's being defined inside of the kube system namespace. The service kube DNS upstream. So defining a different service, presumably. And then we have a config map for our node local DNS. It's all the old salt stuff. I haven't seen this stuff in a while. Right, so this looks very similar to our configuration before, right? This is the node local DNS config map. Looks very similar to our configuration. Configuring a success or denial cache. Denial for 5 seconds, success for 30. Setting the peer local DNS and DNS server. Forcing TCP. Exposing Prometheus on port 9253 instead of 9153. And that means that it will be exposing that port on each host where that pod IP will be located. Configuring the forwarder to use the cluster DNS service. Setting up PTR records, IP6 ARPA. And then here's our daemon set for node local DNS. If you have Prometheus defined as a cluster scope service, it will use this configuration to scrape it. This would be fun to look into. I'm curious like how this would be implemented. So nice. So we're also mounting an xtables lock, probably because the way that this one is implemented, it's actually another consumer of IP tables, configuring IP tables in such a way that it can be used, or that we can capture the DNS traffic. So that is our sample manifest. Let's go ahead and substitute the variables in the manifest with the right values. We are in IP tables mode. Okay. So let's go ahead and walk through this. I want to make this a little bigger so we can kind of see what we're doing here. Right? I'm gonna do that, and then we'll do that. We'll do curl minus LO. Grab our sample. Forgot about that. All right. Okay. Back to our doc here. First thing we're going to do is we're going to figure out domain and local DNS. We're going to figure out the cluster IP, which we already know, 10.96.0.10. We're going to figure out the domain, which we already know, cluster.local. And then this node local address, which will be interesting. The cluster domain is cluster.local by default. Node local is the local listen IP address chosen for the node local DNS cache. Try and go ahead and configure that. So kubedns in our case is 10.96.0.10. The domain is cluster local. And our local DNS service, let's call it 10. Why not? What does it say about picking that address? The local listen IP address for no local can be any IP in, oh, whoops. That's not going to work then. All right. 169.254.20.10. Or any other IP address that can be guaranteed not to collide with any existing IP. This document uses 169.254.20.10 as an example. That'll work for us. So let's go with that. Let's go ahead and hit enter. We'll vim our node local DNS again. So we have now cluster.local configured. We've got our bind. All right. So that configuration looks okay to me. It's all configured accordingly to this configuration. So let's take a look and see what it looks like when we try to apply it. So kubectl run apply -f node local DNS. Looks like it applied cleanly. So then I'm not sure of a way to flush the cache without deleting the pods. I think deleting the pods might be the way to do it. I'm not sure if there's another way. The good news is the cache is only 30 seconds, so it shouldn't hurt you too bad, hopefully. But that's the way it's configured. All right. So kubectl get svc -n kube system. So now we have our DNS upstream and we have our kubedns configuration there. Kubectl get pods -a. We have our node local DNS running. Grep node local DNS wide. We've got one node local DNS running on each of our control planes, or on each of our nodes. Let's go ahead and jump in here real quick. TP. So there we see 169.254.20.10. Node cache listening on port 8080. Don't know what that's about. We have node cache listening on port 53 and on port 53. Again, these are related to PIDs now. Before, likely they were not. That one's interesting. I wonder what that's about. It's definitely an HTTP service. Metrics. Healthy. Why don't we stop guessing and go look? What do you say? Looks like it's the health port. So, oh, it is the health port. So it looks like that's all it is, just a health port, whether it's healthy or not. That makes sense. And in fact, I remember now, seeing it in the deployment, right? That's actually how it determines that that particular guy is in a healthy state. So neat. So then let's take a look at our routing table. We don't have 169 in there anywhere, but we can ping 169.254.20.10. Well, never mind. So we see it running. So let's go ahead and play with it a little bit. So let's go ahead and jump back into our pod again. Worker. Bash. And then we'll do apt update. Apt install bind tools. Utils. Come on, apt search. What is it called in Debian? I know it's going to start with bind. Bind 9 utils. Of course it is. Why wouldn't it be? Install. Yes. All right. So let's do dig Kubernetes any.any.svc.cluster.local at 169.254.20.10. Wait a minute. Install dig. Come on now. Really? That's what it is. Muscle memory for the win. All right. Okay. So we have dig working. Now we can query that 169.254 address from the host. That's where we are, right? We're on kind worker. And we can see that we can query 169.254.20.10 and get a response. And we can do the same thing for 10.96.0.10. Get the response again, right? And now the interesting thing is that we have a cache locally that we're residing against, right? So we can see that we're getting the same response, that there's no difference, right? Unlike what we saw before, we're not getting a different response from a different query. All of our queries seem to be going to the same DNS server. What I'm looking at to determine that is this chunk right here, right? Where we're looking at the defined service times. Before we deployed node local, what we were seeing was difference in the results because the DNS service would forward us to one of the other, the DNS service would forward us to one of the resolving core DNS pods. And so every time we made a request, we would see the response from one of the healthy DNS pods, and the clock would be different between them, right? And so we would see a different result, right? In this case, that's not what we're seeing. In this case, what we're seeing is one DNS server responding to all of the queries regardless. We're not seeing any difference in the resolution. Like if I look up google.com, for example, All right, 30 seconds, 30 seconds. 8, 26, 25, 24, and it's caching that result for 30 seconds. And we're going to be with the same DNS server for all 30 of those seconds, and that DNS server is the one that's running right here on this host. Now what that means is that we have effectively, to your point, Lamati, if we do iptables save, and we look for 10.96.0.10. So destination, got a bunch of no tracks. We got some accepts, which is good. We're sending the result of anything coming from a pod IP address going toward the DNS service. We're kicking it to the DNS TCP cluster IP, kubesystem kubedns, and then just below that, in a more specific way, we're saying if the destination is 10.96.0.10 and the protocol is TCP, then send it to DNS TCP. There's our metrics forwarder. All right, so these rules all look like they're pointing it toward the cluster DNS, which wouldn't have changed. Let's see what it looks like for 169.254. No track, no track. Some accepts and some outputs. Interesting. So now what we're looking into is I'm looking at the kubedns DNS TCP piece and seeing where it's going to forward that traffic, right? Because what I was expecting to see was that it would forward that traffic, it would be somehow hijacked here. But instead, what I see inside of the iptables configuration is a different thing, right? So this is the configuration, the definition of this service. And if we grep for this, we see that it's forwarding back to the core DNS pod, not necessarily our local service. Interesting. So now what I want to take a look at real quick is let's take a look and see if, based on this configuration, if the DNS configuration inside the pod has changed, right? So just like we saw before, run bash equal image equals bash. Let's jump into our pod here. Cat etcresolve.conf. Same configuration for the pod. And then let's do, so no difference there. So what's happening in the IP tables layer, it's changing, are pretty cool. Yeah, let's take a look at that, because that's what I'm missing, is where those rules are. So IP tables -L output. Oh. Okay. All right, this is where I was missing it. So these rules are saying, and this is a somewhat non-intuitive thing about DNS in general, right? It's saying if the output, or if the destination is 10.96.0.10, or the destination is 169.254.0.10, then just forward it to the local port 53 or the local port 8080. But don't forward it to another host. On output, kick this to the port locally on port 53, right? And so if I do again that problem SS-LN, and we do a grep for 53, we can see that we are listening on port 53, right? On that IP address or on 169.254.0.10. So depending on which rule it matches, it's going to forward it to the daemon listening on port 53. Right? So in our output above, we're forwarding to the local port, port 53, using that same IP address, and we're telling it to to bind to our local port. And if we look at the configuration of that from the host, lntup, grep 53, we can see that we're listening locally on port 53 with this node cache process, which is our daemon set, right? This process is running inside of our this is the node cache is the process being presented by our node local cache daemon set. And so what's neat about this is that both of these systems can live in parallel, right? We've defined a configuration that allows us to effectively, on the output chain, grab traffic headed for port 53 and send it to our local definition for 10.96.0.10 and 169.254, this is 2010, and resolve it there, right? And that's why the pod configuration doesn't need to change. And we can dynamically add it to the cluster, which is so cool, right? In this configuration, we're saying in IP tables, when you get to the output chain, when you're right about to send it on the wire, don't. Instead, manipulate the packet and send it and bind it to local, to our local binding of port 53. Which is really, really, really pretty cool. And that's exactly how that's working. And that's why when we do our dig, right, or actually google.com against 10.96.0.10, we don't see multiple things responding. We only see one DNS server responding, right? And we see that because it is actually the local DNS server responding. Well, that's our time today. Okay, that's what I wanted to show you. I think this is a really cool feature, and it really greatly reduces the load on the upstream DNS servers. But understand that the way that this is configured, and I want to make sure we pull up this diagram and just talk about this real quickly before I go. In the diagram for local DNS, boop, boop, forward, which is a great little diagram, right? What's happening here is your pods can make a query of DNS, and we're going to take the output. When we see it hit the output chain, we're going to bind it to our node local DNS cache, and we're going to give you a response if we have it. If it's in the cache response, you're going to get a response much faster. And that DNS query never hits the wire. If we don't know it, then we're going to upgrade the connection to TCP, and we're going to send that TCP connection to kubedns, or the core DNS pods that we know about that exist. And we're going to ask it. And in this way, we could still handle that manipulation, right? That configuration of resolving the test.k8.work case, or the TGI.k8.work domain. I could still define that at my cluster level, and it would still be honored by that local cache, right? Which is really cool, right? This is like kind of the best of all worlds. It gives us the ability to modify an existing cluster without any modification to the pod, and we greatly improve the resilience of our DNS queries because we're landing them locally, and if they fail, then it will fall back. If it's not available locally, then it will fall back to the rule above, where I would send that query up to the cluster. So I wanted to do a little more chaos testing here to kind of dig into this, but like it's really, really neat. Yeah, exactly, Limati. Like this is a killer feature for greatly improving the resilience of DNS on Kubernetes. If you're using Kubernetes, you should really consider using this. It's just an incredible tool. Anyway, that's my time today. I hope you all have a wonderful weekend. I know that I'm going to have a great weekend. I'm going to be hanging with my kid and spending some time with my wife, and I'm planning on taking some time off next week. Thank you. Great to see you all, and I look forward to the next one. The next one I think might be Joe. So tune in next week to see Mr. Joe Bita. I'll talk to y'all later. Great to see you all, and thank you for tuning in.